All right, welcome. Today, we're going to peel back the curtain on reality itself. We're going to look at the invisible rules that control how absolutely everything moves, from a planet spinning around a star to, you just getting out of bed in the morning. And it all kicks off with one kind of weird question.
I know, it sounds like the beginning of a bad joke, right? I mean, one is this massive, thunderous explosion of power, and the other is, well, it's the poster child for doing absolutely nothing. But what if I told you that they are both playing by the exact same set of rules?
That's right. All the unbelievable complexity of motion in our universe, it all just boils down to three foundational laws, figured out centuries ago by Isaac Newton. And trust me, by the time we're done here, you are going to start seeing them everywhere.
So, let's dive in with Newton's first law. This one is all about a quality that I kind of like to think of as the universe's stubborn streak, or you could even call it its fundamental laziness.
I mean, really think about that for a second. For thousands of years, people were convinced that things needed a constant push or pull just to keep moving. But Newton came along and said, nope, that's not quite right. It's more like objects, they just resist change. They want to keep on doing whatever it is they're already doing. So why is that?
The whole answer boils down to one simple word: inertia. This is a fundamental property of matter itself. It's not something an object does, it's something an object is. You can think of it as the physical measure of its own stubbornness.
An inertia basically has two sides to its personality. So you take that sleeping cat, right? That's the perfect example of the first part. An object at rest is going to stay at rest unless some outside force, like you giving it a little nudge, comes along. The other side of the coin is that an object in motion, say a satellite way out in deep space, is going to keep moving in a straight line at the same speed pretty much forever unless some other force gets in its way.
And here's the crucial part. Inertia is tied directly to an object's mass. A bowling ball has way more mass than a tennis ball, right? So it has more inertia. That means it's harder to get the bowling ball moving in the first place. And it's a whole lot harder to stop it once it's going. It's just more stubborn about changing what it's doing. Now, this whole idea of stubbornness leads us right into Newton's second law. And look, you've probably seen that famous little equation, F equals ma. But it turns out that's not quite the whole story.
Yeah, this one. It's got to be one of the most famous equations in all of science. You've seen it on t-shirts, you've heard it in movies, and it's so elegant, so simple. It tells us that if you want to make a mass accelerate, you've got to apply a force. The bigger the mass, the more force you're going to need. Seems straightforward enough.
But what if I told you that this super famous equation is actually just a special case? That it's really a simplification of a much deeper, more fundamental idea that Newton actually came up with?
And here it is. This is Newton's actual second law. He said that force is equal to the rate of change of momentum. Now, momentum is just a fancy word for an object's mass times its velocity. Basically, it's quantity of motion. So force isn't just about changing speed, it's about changing this total amount of motion. So, how do we get back to the formula we all know and love? Well, the full-on equation involves the rate of change of both mass and velocity. But, in most of our everyday lives, the mass of an object doesn't really change. So when the mass is constant, you can basically pull it out of the equation. And that leaves you with mass times the rate of change of velocity, which, hey, that's just acceleration. So F equals ma is the version that works great for cars and baseballs, but it totally breaks down for something like a rocket, which is constantly getting lighter as it burns through its fuel.
Okay, on to the third and final law. And this one describes this beautifully symmetric little dance that forces are always doing. They always come in pairs. It's all about a universal give and take.
You've done this, right? It's such a simple experience, but have you ever stopped to think about what's really happening? You push on the wall, and you can literally feel the wall pushing right back on you. The wall isn't thinking about it. It's just a fundamental law of physics happening right there.
And that leads us to this famous, almost poetic phrasing. Anytime one object exerts a force on a second object, that second object, at that exact same instant, exerts a force back on the first one. And that force is equal in strength and points in the exact opposite direction.
Now, here's the part that trips a lot of people up, so this is really important. The action and reaction forces are always acting on different objects. Your push is on the wall. The wall's push is on you. And that's the key reason they don't just cancel each other out. It's why you can actually feel it.
And once you know this, you see this principle everywhere. A rocket shoves hot gas down, that gas shoves the rocket up. A cannon fires a cannonball forward, the cannonball kicks the cannon backward. That's recoil. These aren't two separate things happening. They are two halves of the very same interaction.
Okay, so we've got these three fundamental laws down. Now let's just quickly see how they actually play out in our world through a few of the most common forces we deal with all the time.
Let's just break these down really fast. First up, you've got gravity. That's the constant pull the Earth has on pretty much everything. Then you've got tension, which is a pulling force, like what you'd feel on a rope that's being pulled tight. And finally, there's the normal force. Now, normal here is just a math term for perpendicular. This is the pushing force a surface exerts to keep something from falling right through it. It's the force that the wall pushes back on you with.
So let's bring this all home. We've got inertia, this deep link between force and momentum, and the fact that every action has a reaction. Put them all together, and these three simple rules form the entire foundation for what we call classical mechanics. So, if you're going to remember this, here's the easiest way. Number 1, objects are lazy. They resist change. Number 2, if you want to overcome that laziness and actually change an object's momentum, you've got to apply a net force. And number 3, every single time you apply that force, the object you're pushing on is going to push back on you just as hard.
From the way the moon circles the Earth to the simple act of taking a step, these three laws are always running in the background. So the challenge for you now isn't just to know them, it's to start seeing them for yourself in everything that moves. What are you going to see first?